free response questions for our solutions chapter. This is really long, and I will post in the description at what time each question starts. So just pay attention to that if you don't want to have to watch this whole thing, because YouTube gave me the permission to make a long video, so I'm going to make long videos. So for number 1, here, let me get this. So, okay, this is number 1, and the question asks us, well, you can read the question. I'm just going to start writing just to save time. So the reason that these guys have these different freezing points and these different electrical conductivities is because I'm just going to put electrical, E for electrical. You should probably spell it out. Electrical conductivity corresponds to higher freezing point depressions which I'm just going to abbreviate from here on out as FPD. So higher electrical conductivity means a higher freezing point depression or a higher change in the freezing point. And so the reason that sucrose is the lowest is because sucrose doesn't ionize. So it's going to have a Van Hoff factor of just 1, which means since the change in freezing point is equal to the freezing point constant times molality times I, this one having an I value of 1 means it's going to have, based on these guys, the lowest change in freezing point. Whereas formic acid, it doesn't completely ionize, it only partially ionizes, so it's going to have an I value of like 1 point something, which gets this guy to be just a little bit higher. Sorry, I didn't write this down. And then the last one, the sodium formate, actually will completely ionize into 2 separate ions, the sodium ion and the formate ion, and so it will have an I value of 2, which means it will have the highest change in freezing point of them all. And that's kind of really all there is to this one. This one's an old question, so it's kind of a weird format, but, you know, it's a good question nonetheless. Come on. Oh, I gotta hit the... Sorry, I'm still working all the kinks of this out. Okay, let me do, I think this is what I want to do next. And erase all that. Yes. Okay, moving on to question number 2. Alright, so we have a solution. And the first question asks us to find the molecular mass. They would call this mass. Now they wouldn't call it weight anymore. This is, again, an old question. Find the molecular mass of this compound. They give you all that great information in there. And so the way that you figure this out, first you want to figure out, I like to kind of list everything I have, and so that's what I'm going to do first, actually. So the freezing point depression is equal to the freezing point constant times molality times the Van Hoff factor. And in this particular case, our actual freezing point depression was 0.97 degrees Celsius. They told us that our freezing point constant, 1.86 degrees Celsius per molal. And then we actually need to find out what our molarity is. And we know that we have a non-electrolyte. It says up there, right here, it does not conduct electricity, so I is equal to 1, which means we don't have to deal with it. So I'm going to start first by finding out what molality is equal to by solving this equation right here. So molality is equal to the change in freezing point divided by the freezing point constant. So my change in freezing point was 0.97. My freezing point constant was 1.86, and so this works out to a molality of 0.52. And remember, the units for molality are moles of solute per 1 kilogram of solvent. It helps to keep track of your units whenever you're solving for these things. And so then they told us that we actually used, let's switch colors here, 3.0 0.23 grams of the solute. And so we need to find the molar mass. Molar mass, of course, is grams of, in this case, the solute over moles of solute. Well, we have grams right here, so I'm going to start this little calculation and stick my grams on top. I know that this is my molality, and since I have moles of solute right here, well, I'm going to put that on the bottom, 0.52 moles of solute over 1 kilogram of solvent. Now, of course, now I have to get rid of this mass of solvent, so I'm going to look back up in the question, and it told me that I used 100 grams of water, which is 0.1 kilograms of the solvent. So now my kilograms of solvent cancel out, and I plug this into the calculator, and I get 62 grams per mole. So that's A. And then B says, gives me all of the percentages and says, find the actual molecular formula of the compound. So that's what we're going to do next. Let me erase some of this stuff so I got some more room to work. Okay, so just a refresher, our molar mass was equal to 62 grams per mole. Whenever you're given percentages, remember you just make your assumption that you have 100 grams of whatever substance it is that you're dealing with. And so you take all of these percentages and you convert them to grams. So we say we have 9.74 grams of hydrogen, 38.7 grams of carbon, and 51.56 grams of oxygen. Divide each of them by their molar mass. So molar mass of hydrogen is 1.01, carbon is 12.01, and oxygen is 16.00. And the reason that we're doing this is to convert grams to moles because, of course, a compound is the elements with the mole ratios, you know, how many moles of each element, written as the subscript. And we've got to get them to moles. We don't do compounds that have mass ratios. That just wouldn't make sense. And so this works out to 9.64, this is 3.22, and this is 3.22. So to get this to the lowest whole number ratio, we divide all of these by the smallest, which in this case is 3.22, and so this becomes 3, this becomes 1, and this becomes 1. So our empirical formula is going to be, let's see, CH3O. Always write your carbon first, and oxygen always comes last, so plop hydrogen down there in the middle. So the question didn't ask us for the empirical formula, it asked us for the molecular formula. So in order to find the molecular formula, you take the mass of the empirical formula, which in this case is going to be 12, and 3 is 15, and 16 is 31. So this has a mass of 31 grams per mole. Compare it to your molar mass. So our molar mass is actually 62 grams per mole. Our empirical formula is exactly 1/2 that. So to get from the empirical formula to the true formula, just take this whole thing and multiply it by 2. So our molecular formula, there's something very funny to me about getting to write MF on a chemistry problem. You can chuckle with me on that one, and if you don't get it, it's because you're a good boy or girl. So the molecular formula of this guy is C2H6O2. So part B, done. Now you gotta do part C. Complete combustion of this thing. They want to know what's the pressure of the gas mixture after everything is all said and done. So let's figure that out. Okay, so they said that we used 1.05 grams of our sample. I'm just going to call it CHO. We know that it has a mass of 62 grams per mole. And then they want to know about the gas mixture, the resulting gas mixture of water and carbon dioxide after it's all done. So I need to figure out, well, if I have, you know, this many grams of CHO, the C2H6O2, whatever it was, I need to know how many moles of water and carbon dioxide that I'm going to form. So to do that, I have to have a balanced reaction. So we were at C2H6O2. We're going to combust it, which means we react it with oxygen. And it says we're going to produce CO2 and water. So to balance this reaction, y'all can work that out. I'm just going to write it down. It's 2, 7, 6, and 4. So for each, see, I'm in moles of CHO right now, so for every 2 moles of CHO, I'm going to get a total of 10 moles of gas, because I'm going to get 6 moles of carbon dioxide and 4 moles of water. So total moles of gas is 10. And remember, whenever you're working with gas mixtures, the identity of the gas, it doesn't matter. They all contribute to the pressure of the overall mixture. Not equally, I'm not going to say that, but they all contribute to it. So it doesn't matter exactly that we have 6 moles of carbon dioxide and 4 moles of water, or water vapor. It just matters total number of moles, not what they are. So this works out to be 0.0847 moles of gas. And then it says, what's the pressure of this gas mixture contained in 3 liters at 127 degrees Celsius? I have volume, I have temperature, I have moles of gas. That tells me that I need to use PivNert. Gotta love PivNert. And since the question is, what is the pressure? I'm going to rearrange this equation and solve for, actually no, I'm just going to plug numbers in. So my pressure is my X, my volume is 3, N is what I just calculated up here, number of moles, so 0.0847. R is always 0.0821. And our temperature, they gave it to us in Celsius. We can't use Celsius when we're dealing with the gas constant R. We have to use Kelvin. So 127 degrees Celsius plus 273 tells us that that is 400 Kelvin. So, oh crap. I hate it when it does that. Sorry. Okay, 400, it gets stuck sometimes, Kelvin. So solve all this and we get that the pressure is equal to 0.927 atmospheres. And that question is done. Yay us. So let me get rid of this guy. And all of the work that we just did. Trash. Get rid of that. And those little 2 boxes that have been bugging me. Okay, next question. Okay, maybe I can read that just fine. Read through the question, and I'm just going to start working it out. So the first thing asks us to find that empirical formula again. So we make our 100 gram assumption, 93.46 grams of carbon divided by the molar mass of carbon gives us 7.797 moles of carbon. And then it said that we had 6.54 grams of hydrogen divided by its molar mass. Means that we have 6.48 moles of hydrogen. This is carbon, and this is hydrogen. So to get this into simplest whole number ratios, we divide it by the smallest one. So divide both of these numbers by 6.48, and this one becomes 1.2. This becomes 1. That's not a whole number, so to get rid of a 0.2, we multiply both of these numbers by 5, and this becomes a 6, and this becomes a 5. So our empirical formula is C6H5. Now B, I'll switch colors here just to keep it interesting. We have our solution, and now they want to know the molality of our p-dichlorobenzene solution. So just to refresh your memory, molality is moles of the p-dichlorobenzene, I'll just call that PD, divided by it's not really divided by, over kilograms of our solvent, which is in this case the naphthalene, so I'll just call that nap. So first of all, let's figure out how many moles of the p-dichlorobenzene. They said that we used 2.53 grams of the benzene, and it has a molar mass of 147 grams per mole. So that tells me that we have 0.0172 moles of the p-dichlorobenzene. Then we need to figure out how many kilograms of the naphthalene we have. Well, they told us right here we're using 25.86 grams of naphthalene, which is, move this over 3 times, 1, 2, 3, 0.02586 kilograms of nap. So we just take our moles of the benzene, divide it by kilograms of naphthalene, and we end up with a molality of, ooh, this ugly number. That's a bad number. I don't like that number. Okay, moving on to C. C wants us to know the freezing point depression of the naphthalene. So if you remember your formula, and this would be on the formula chart when you're actually doing the free response section of this, that the freezing point change is equal to the freezing point constant times molality times the Van Hoff factor. Well, this is a hydrocarbon, which are not electrolytes, so I will go away. And since they're wanting to know the freezing point depression, then we just rearrange this and say that Kf is equal to the change in the freezing point divided by the molality. First, to find the change in freezing point, they said that the pure naphthalene is 80.2 and the new solution has a freezing point of 75.7. So the change in temperature is going to be the 80.2 minus the new freezing point of 75.7. And then from there, we just divide it by the molality that we calculated right there. So divide that by the really bad number. Sorry, I know that's kind of corny. And you end up with a freezing point depression constant of 6.8. And the units on this would be degrees Celsius per molau. And then for D, I'm going to have to erase because I ran out of room. Trash. Okay. D asks us to calculate the apparent molecular mass of the unknown hydrocarbon. So we, now looking at the new one, let's see, it freezes at 76.2 now instead of the 80.2. So again, the change in the freezing point is equal to the freezing point constant times the molality. This time, we don't know the molality. We know the change in freezing point. It's just 80.2 minus 76.2, or 4 degrees Celsius. We know the freezing point constant. It's the same as what we calculated in the last question of 6.8. We don't know molality. So solve this for molality, and molality is going to equal, where is that, 0.59, and keep in mind the units on molality are moles of, in this case, the unknown hydrocarbon. I'm just going to call it CH, over 1 kilogram of, are we still dealing with naphthalene here? Yeah, nap. This stuff stinks to high heaven too. This is the main ingredient in mothballs, and just in case you were wondering. Okay, so then they told us in the question that we use 2.42 grams of this unknown hydrocarbon. We're trying to ultimately get the molar mass, which is grams per mole. So we're going to use that 2.42 grams of our hydrocarbon. Set up one of these little guys. Since we know how many moles we're dealing with, 0.59 moles of hydrocarbon per kilogram of naphthalene. Well, to get rid of the kilogram of naphthalene, we need to know what the mass of naphthalene was that we used, and that is right there, but it's in grams, so scooch that decimal over 3 spots. And kilograms is on top here, and I got this nice empty spot on bottom right here where I can put my mass. So 0.0267 kilograms of naphthalene. And so my kilograms of naphthalene cancel out. I'm left with grams of hydrocarbon per moles of hydrocarbon, which is exactly what I want to be in. So my hydrocarbon unknown, hydrocarbon has a molar mass of 154 grams per mole. And then the last question says, what's the molecular formula of our unknown hydrocarbon? Well, way back up here in part A, we figured out that the hydrocarbon has an empirical formula of C6H5, which would have a mass of 72 plus 5 is 77 grams. And so 154 divided by 77 tells us that this is half of this, which means that our empirical formula is half of what it should be. So the molecular formula is C12H10. And that question is done. Oh, that mess out of the way. Okay, next question. This is going to be the longest video ever. It's okay, y'all asked for it. Okay. Next question deals with sulfuric acid and dilutions, and looks like a little bit of a neutralization. So whenever they are talking about a dilution, right here, you get to use M1V1 equals M2V2. So our original molarity was the 18.4. The volume of our concentrated stuff is what we don't know. The final molarity is the 5.2. And our final volume that we want is 1 liter. So solve this for X. And the volume that we will need on this is 0.283 liters, so not very much at all. And then B, I'm going to change colors. B asks you to figure out the mass percent. Well, remind yourself of the units of mass percent. That's mass of, in this case, H2SO4 divided by the mass of the whole solution. So we know, let's see, what can we figure out? We can figure out the mass of our H2SO4. Knowing that we used 0.283 liters of this particular, or does that even matter? Now let's just take our 18.4. Oh, dang it. I hate it when it does that. It's very annoying. So 18.4 moles of H2SO4 are contained in 1 liter of solution. Mass percent in the original concentration. So 18.4 moles contained in 1 liter. We're just going to assume for simplicity's sake that we have a liter of solution. Well, I know that every mole of H2SO4 has a mass of 98.1 grams. So this right here, we're now at grams per liter. Well, I don't want grams per liter of solution. I want grams per grams of solution. Mass of H2SO4, mass of solution. So I got mass of H2SO4. So to get from liters of solution to mass, I'm going to come back up here and use my density. So my density is for every 0.001 liters of solution, I have 1.84 grams of solution. And so now my liters cancel out, my moles cancel out, And I'm left with mass of H2SO4 over mass of solution, which is exactly what the question asked us for our answer in. So solve all those numbers, and you get 0.981. And this is like, I don't know, it's not a percentage. To get this into a percentage, you just simply need to multiply this by 100. So H2SO4 is 98.1% actual hydrogen sulfate, and then what, 1.9% water. No wonder this stuff smells so bad. All right, so for C, I need to erase to make some more room. Trash. Gotta love that. I love this little program. Okay, for C, let's change colors again because that's fun. All right, C wants you to calculate the volume that can be neutralized. Well, if we're neutralizing something, then that tells me that I'm going to need an equation. So my H2SO4 is going to react with sodium bicarbonate. And look at that, they're nice enough to give us the formula. NaHCO3. And we are going to produce. As soon as I see I'm using a carbonate and I'm neutralizing it, I know that I'm going to make some CO2. I also know that this is a neutralization, so I'm going to make water. And I also know that I'm going to make a salt. Well, here's my cation, here's my anion, so my salt is going to be sodium sulfate. So now to balance this guy, y'all can figure that out. And it's going to be 2 here, 2, and 2. Now, the question said 10.5 grams of sodium carbonate will neutralize what volume of our diluted sulfuric acid? Well, this is just your basic stoichiometry problem. So I have 10.5 grams NaHCO3. Set this up. NaHCO3 has a molar mass of 84.01 grams per mole. Oh, it's sticking again. I don't know why it does that. And then for every 2 moles of NaHCO3, we're going to react 1 mole of H2SO4 according to our reaction up here. And our molarity is for every 5.2 moles of H2SO4, SO4, we will have 1 liter of the solution. Alright, so grams of NaHCO3 cancel out, the moles cancel, moles of H2SO4 cancel, we're left with liters of solution, which is exactly what we want. So plug this into your nifty little calculator and you end up with 0.0120 liters of solution. Okay, switching colors again. Let's go back to red. For D, what is the molality? Remember that molality is moles of solute, in this case H2SO4, over kilograms of the solvent, which is in this case H2O. So this is what we need to figure out. So the 5.20 moles of H2SO4 tells us that we have 5.2 moles H2SO4 in 1 liter of mixed solution. So what I'm going to do, I'm going to first convert my liters of solution to mass of solution, since I ultimately need to get to mass. So every liter of solution, according to the density that's right here, 1.38 grams per milliliter. Well, I have a liter, so I get to multiply this by 1,000. So 1 liter of solution is going to have a mass of 1,380 grams. Okay? Then I can figure out exactly what mass this 5.2 moles of H2SO4 has by taking that 5.2 moles H2SO4 and converting this to mass using every mole has a mass of 98.1 grams. And that works out to 510 grams of H2SO4. Well, this is grams of H2SO4 and water. This is just my H2SO4. So if I take my 1380 and subtract 510, well, now I have my mass of water, which is 870 grams. Take this, plug it in back over here. I know that I have 5.2 moles of H2SO4 over 0.870 kilograms of water. And so that ends up working out to 5.98 molar H2SO4. 2 left. Wow, this is going to be every bit of like a 50-minute video. That's so crap. Oh crap, don't do that. Oh, I almost deleted everything. Okay, sorry about that. Let me get all of this erased. Those weird little lines erased because we don't want those anymore. Oh, shoot, I keep doing that. Sorry. Okay, 2 more questions left. And this one looks a lot like the one we did, not this last one, but the one before that, where first you're finding the empirical formula, then you're finding the molar mass, then the molecular formula, and then they ask you to do a couple other things with the gas aspect of it, which is always nice. Okay, so A, find the empirical formula. Let's see, we got 65.60 grams of carbon, we got 9.44 grams of hydrogen, and they didn't give us a percentage of oxygen, but you know that all these percentages are going to add up to 100, so that means we have 24.96 grams of oxygen. Divide that by 12.01, divide this by 1.01, and divide this by 16. So this one equals 5.462. This one is 9.35. And this one is 1.560. So this becomes, divide all of these by the smallest, so you get whole number ratios. This is 3.5. This one becomes 6, and this, of course, becomes 1. We can't have 3.5, so multiply all of these guys by 2. 7, 12, and 2. So our empirical formula equals C7H12O2. B asks us to find the molar mass and the molecular formula of the compound. So our delta T says it froze at 15.2 Celsius degrees below the normal freezing point. So they just right there told us that delta T is 15.2. And then we know that the mass of our CHO compound is 1.570. And we know that the mass of our camphor, I don't know how you pronounce that, is 16.08. This is grams, degrees Celsius. And then they told us that our freezing point depression constant was 40.0 degrees Celsius per molal. So first thing I want to find is my molality, and that's equal to delta TF. Oh, freaking A. Delta TF, I'll change colors just so it's easier to read, divided by the freezing point depression. So 15.2 divided by 40. And that gives us a molality of 0, for the love of God, 0.38. And then remember the units on this are moles of the CHO over 1 kilogram of the solvent, which in this case is camphor. And so from here, we can figure out the molar mass. Take our mass of the CHO, 1.570 grams of CHO. And we're going to put the 0.38 on bottom. The 1 kilogram of our solvent on top. And they told us the mass of our camphor was 16.8 grams, so scoot that over 3 spots. 0.01608 kilograms of CAM. So that cancels out. We're left with grams per mole. And this works out to mathematically 257 grams per mole. So looking back up here, to find the empirical mass of this compound, it just so happens to be 128, which is coincidentally, ooh, class is over, haha. Sorry about that. I know that's kind of annoying. This is about 1/2 of this, which means this is 1/2 of the real thing. So the molecular formula is C14H24O4. So I'm going to erase all this so I can do C and D. Alright, C tells us they want to know the molar mass based on all this gas information. So they gave us temperature, they gave us pressure, they gave us volume, we have grams. Well, that tells me that I'm using Pivum Mert, where the pressure is 1. Love that. Volume is 577 milliliters, but remember you can't use milliliters when you're using a gas constant. You have to use liters, so we're going to go 1, 2, 3. Say that this is 0.577. Molar mass is what we're trying to find, so that's our X. Our mass is still the same, 1.57. R is 0.0821. And 300 degrees Celsius, remember we can't use Celsius, so 300 plus 273, 573 Kelvin. Solve all this for X, and our molar mass in this case is equal to that same 128 we had for the empirical formula, which is odd, grams per mole, of course. Which leads us to D. Briefly describe what occurs in solution that accounts for the difference between the 257 that we got here for part B and the 128 that we got here for part C. Well, there's two possibilities. The first possibility is that either whenever the compound comes into contact with the camphor, it dimerizes, as in forms a dimer, doubles up. Or the alternate explanation is that it is naturally at this 257 grams per mole, but when it becomes a gas, it dissociates. So, two possibilities. Either it dimerizes in the camphor, or, not both, there's no and in here, it's definitely an or, it dissociates in the gas phase, one of those two things. And I think I'm going to go ahead and call it quits. That last free response question we can talk about in class if you want. It's a qualitative question, so it's not really that, there's not that much to it. So that would be the end of that. 38 minutes.